Tak nampak Anis.
Okay.
Assalamualaikum warahmatullahi wabarakatuh. We are from K2 Group 17. Our name is aura.co, and today we want to present about wastewater treatment plant, and the location is prepared as the Bandar Estate. This is our organization chart. I'm the CEO. My name is Nur Ida binti Muhammad Yusof. My matric number is 71515.
Next, I am Secretary and Design K2. My name is Nur Azra binti Ayub. My matrix number is S72139.
I am Information Collector. My name is Siti Nazhani. Matric number S71121.
And I'm the Expert Engineer. My name is Anis Farahi. And my matric number is S69979.
This is our step of design process. First, briefing and planning. Second, collecting required information. Third, define problem statement. Fourth, identify suitable method. 5, calculation design. 6, design unit operation. 7, supervision and final design. And last, submission and presentation.
Next is treatment plant locations. Our group choose Bandar Baru and Stacks as the inspiration for our group project, which we name Bandar Aura Estates. So we modified the original plan and add some input to make it fit for our project needed. After this change, the area is 6.78 km square, and the population have 30,300 PE. So at the Bandar Baru Aura Estate has facility which is housing estates, school, commercial area, light industry, public facility, and so on.
Okay, the next part is methodology of this design. Before we start the design process, we need to calculate first. We need to calculate such as diameter of the sewer, the velocity, and extra. We calculate using the Excel. In order to calculate, we need to have optimal parameter that refer to Malaysian Standard Industrial Guideline MSIG Volume 3, 4 and 5. After get the all value needed, we proceed to the design process using AutoCAD. Okay, so this is our final design of first unit operation, which is sewer. Ductile iron pipe was selected due to its high strength, durability and resistance to impact and heavy traffic load, making it suitable for urban and industrial area for bandar and stack. The hydraulic design parameter including flow condition and pipe capacity were assumed based on Malaysian Industrial Guideline MSIG Volume 3 recommendation. Our PE is 13,300 and we calculate the FP, DWF, Qmin and Qmax. D over D full, we use 0.7, which represent a recommend operating condition that ensure efficient flow while preventing surcharge. And then Q over Q full and V over V full, we get based on mailing formula. We plot the graph, and then the N and S value based on ductile iron pipe. And the output we get diameter for this sewer is 0.4875 and we round up to 0.5 meter. Is the design. And then the radius half of 0.5. So this design is acceptable because the V min is in a range of 0.621. We get it at 0.6559, and for the V max, we in a range also, which is 1.4108. The range should be in 0.8 to 4.9 meter per second. Okay, so this is our final design of first unit operation, which is civil. Ductile iron pipe was selected due to its high strength, durability and resistance to impact and heavy traffic load, making it suitable for urban and industrial area for bandar and stack. The hydraulic design parameter including flow condition and pipe capacity were assumed based on Malaysian Industrial Guideline MSIG Volume 3 recommendation. Our PE is 13,300 and we calculate the FP, DWF, Qmin and Qmax. D over D full, we use 0.7, which represent a recommend operating condition that ensure efficient flow while preventing surcharge. And then Q over Q full and V over V full, we get based on mailing formula. We plot the graph, and then the N and S value based on ductile iron pipe. And the output we get diameter for this civil is 0.4875 and we round up to 0.5 meter. Is the design. And then the radius half of 0.5. So this design is acceptable because the V min is in a range of 0.6 to 1. We get it at 0.6559, and for the V max, we in a range also, which is 1.4108. The range should be in 0.8 to 4.9 meter per second.
Next, after the civil operation, we have unit operations for screening. As we know, screening is a primary treatment unit used to remove lush solid from wastewater. So this is our design. Our design have the blade spacing, blade thickness, and blade width, lush, and so on that we determine through calculation and refer to National Standard Industry Guideline Volume 4 Table 4.10. So if we look at here our calculation, we have a number of blade, we have 7. Width we got 0.2 meter. Size of the opening 0.25 meter, and lastly blade thickness we have 0.1 meter. So we design a straight type screening system in 3D designs. So why we choose straight shape design? Because the shape design had to treat large debris effectively. At the same time, as a wastewater flow down the step, it provides natural aeration, which increase oxygen. Which is increase oxygen in the water. So this unit help to protect downstream unit and improve overall treatment efficiency. Okay, that's all.
Yay! Our unit operation is the bridge chamber. This is the final result of the bridge chamber. The primary objective is to remove a heavy inorganic solid like sand, gravel, and silt via gravity sedimentation. These designs we are complying with MSIG Volume 4 Table 4.14. The key design features is the main body is the 6 meters times 3 meters. This is for optimized dimension to maintain horizontal flow velocity. The V-shaped hopper 1.225 meters, designed for centralized grid collection and efficient discharge. The importance of this grate chamber is to prevent mechanical wear, which is abrasion on downstream pumps, and avoid sediment build up in the subsequent treatments tanks. This is the calculation for grate chamber. We calculate for the volume, width and length. Next is the grease removal. This is our final result for the grease removal. The grease removal is the objective is separation of fats, oil and grease using the buoyancy principle. For this design standard, for the grease removal, we choose this complying with MSIG Volume 4, Table 4.15. This grease removal, the mechanism of treatment is the multi-buffer system. This multi-buffer and its the function is to break flow energy and reduce turbulence to allow particles to rise. This we use for the length is 6 meter and for width is 1.3 to 5 meter. This is for the provide sufficient detention time for grease to float to the surface, and the grease remover is important to prevent pipe clogging and ensure the biological treatment stage is not compromised by oil films that block oxygen transfer. The special part is we put the skimmer in there. Is the function is to showing how the floating oil is separated from the clean air, which is from this water is enter this, and the oil is stay on this buffer. So when the water is rise and that can separate the oil and water go to the next buffer. And this is the calculation for search for the volume and the PE for this calculation.
Dah. Okay, boleh.
Okay, for the primary clarifier, we need to understand few key functions before we go deep through the design. First, we need to understand the solid liquid separation, where the gravity pull down the particle that is heavier than water at the bottom of the tank. Second is load reduction, where we reduce the concentration of the particle and let it sit before they reach the aeration tank. Third is the equipment protection, where primary clarifier or primary sedimentation help to prevent heavy grade or solid from clogging the pump or interfering with the micro activity that will happen in the next stage. So there is several things that we need to make sure before we design our primary clarifier. Is first, we need to make sure it follow the standard of MSIG compliance 4.18. Next is the optimized ratio. As you can see, the ratio is 4:1, which is the length of the tank must be long enough to help the particle to settle down. Next is the effective solid removal. So we need to make sure that our clarifier is effectively help to remove the solid, and we need to prevent the turbulence, which is when the water is wavy and may slip out from the tank. Next is the standardized geometry, where we use all the calculated length, weight and volume to design our final design. Okay, so for the aeration tank, first of all, before we start, we need to understand the function of the aeration tank. First, the key function is to for the oxygenation, which will provide the essential oxygen to for metabolism. Next is the oxidation, where we facilitate and break down the BOD. And next is the suspension, where we prevent the biomass from settling at the bottom of our tank. So, for the design explanation, as you can see here, this is our result. First, we comply to MSIG Volume 4, Table 5.2, which is stated that every aeration tank needs at least two aeration tanks for wastewater treatment plant. So this is the design for one aeration tank, but in the overall plan layout, we need to have 2 aeration tank. Next, the operational continuity, which is when we use 2 aeration tank, if for example aeration tank A have problem or in undergoing maintenance, aeration tank B can still cover the work. Next, the optimal oxygen transfer. So when we design it in this way, it can help to transfer the oxygen in the most optimal way. And next, we also add the baffle wall. As you can see here, the baffle wall is used to make sure that the tank is not short circuit, because if the water overflow, it can disturb the overall function. Last but not least is standardized geometry, which we follow all the length, volume that we have calculated in order to produce this design. That's
Next, before this we share about primary clarifier, but this time I will share about secondary clarifier. Primary and secondary clarifier is the same. It have the same function, but secondary clarifier is enlarged in size to handle higher sludge volume after biological treatment. So this is our designs. The design and calculation we carry out based on Malaysia Standard Industry Guideline Volume 4 Table 5.10. So if we can see here, at retention time, secondary clarifier have a bit fast compared to primary clarifier, which is 1.5 hours. So function is to separate biological sludge from treated wastewater through sedimentation. So this is our design. This is a length, the 33.2 meter and 11.07 meter for weight. So compared to the primary clarifier, this unit include a mechanical system that help to push the settled sludge towards the sludge outlet tanks. If we look at this design, this here is a mechanical system that push the settled sludge toward to sludge outlet tank. This is outlet tank. So this mechanical movement improves sludge collection efficiency and prevents sludge accumulation at the bottom. So the clarifier water then flow up as treated effluents. That's all.
Okay, for the overall plan operation layout, as me and my friend already presented just now, we have completed most of the unit operation, and right now we are focusing on combining all the unit design into one treatment plan. But before that, we need to make sure that we have the most smooth and also clearest piping route, and also we need to make sure that our treatment plan fit into the designated area that we have decided for Bandar Aura and Start. And as we can see in this picture, this is the idea or reference that we may use in our overall plan operation layout that we will share on our final report.
Okay, for the business opportunity, the proposed design offer a practical and scalable solution that comply with environmental regulation while improving treatment efficiency and effluent quality. From an commercial perspective, this project presents a strong business opportunity as wastewater treatment services are essential for municipal, residential development and industrial facilities, and can be commercialized as a consultancy service or modular treatment system. In conclusion, the final wastewater treatment plant design has successfully achieved all the objectives that outlined in the proposal. The design incorporates appropriate unit operation that comply with relevant Malaysian standard and environmental regulation while ensuring efficient treatment performance.
That's all from us.
Thank you.